All right, so we're going to look at the 2018 AP Chemistry Free Response problem number 1. We're going to just go right into it, unless if you have not pulled this up and looked at it and worked it on your own, maybe pause this video. You can find it just by Googling 2018 AP Chem Free Response and use your equation sheet and calculator to go through and try to answer this problem on your own. Then come back to this video. Look along as I explain the different answers and how the points are distributed. So number 1 says, a student performs an experiment to determine the value of the enthalpy change of a reaction for this reaction up here. This piece of paper, the printer didn't show quite everything, but I'm just going to use it and put in what needed to be added. First thing is to determine the oxidation number of chlorine in NaOCl, sodium hypochlorite. So NaOCl. We're going to look at this a couple of different ways. So the first way is to remember the sum of the applications of the oxidation numbers in a neutral compound equal 0. I also am going to take an opportunity to look at this just from chlorine in the perspective of it being in this polyatomic ion, hypochlorite, that has a 1- charge. So the applications of the oxidation numbers will equal that. So we're going to start here because it's a little simpler. Oxygen and chlorine are bonded to each other in this polyatomic ion. And our oxidation number rule for oxygen says that oxygen is usually a -2. So, and this is not one of the exceptions, not a peroxide, not bonded to fluorine, which means quite simply chlorine has to be a +1 for the applications to equal the charge. Up here, all that holds true. Oxygen is bonded to the chlorine, so it's still -2. The sodium has an ionic force of attraction to the entire OCl1-, and alkali metals, as we discussed when we went over oxidation numbers, are a lot of the time +1. So for this to work, chlorine still needs to be +1. So that's our answer for part A. Chlorine has a +1 oxidation number. So B, calculate the number of grams of Na2S2O3 needed to prep 100 milliliters of 0.5 molar sodium thiosulfate. And it was 5 sig figs in the volume, 3 sig figs in the molarity. Paying attention to sig figs, we're going to be using 3 sig figs for answers here because that was the smallest number of sig figs given to us. So it was 0.5 molar sodium thiosulfate, and it was 100 milliliters. Let me add a couple more zeros there, just for the 3 sig figs we're paying attention to. And so 0.05 moles, actually 0.0500 moles of sodium thiosulfate is what we get. And then for the grams, we would grab our periodic table, add up the molar mass. And when we do that, the molar mass turns out to be about 158.1 grams per mole. So we multiply, and when we do 0.05 times 158.1, we get 7.905, and to 3 sig figs, I rounded just a little bit, it would just be 7.90 grams of sodium thiosulfate for our answer for B, part 1. Part 2, straight to C actually, part 2 wants us to use this chart and the balanced equation to determine which is the limiting reactant and justify our answer. So when we do that, well, it's all 5 milliliters and all 0.5 molar. So 5, and we'll convert to liters, 0.005 liters times the molarity. These are all 0.0025 moles. Remember that for a little later in this problem, but they're all 0.0025 moles. So, coefficient of 1, coefficient of 4, coefficient of 2. NaOCl is our limiting reactant. We are supposed to justify our answer. It doesn't specifically say we have to do it with math. You could just write down NaOCl is the limiting reactant. We have equal numbers of moles for all reactants. Therefore, the reactant with the greatest coefficient will run out first, and it is the limiting reactant. You could also, do the math to show, convert to one of the products, show that the amount of product made, let's say water from each of these NaOCl would be the smallest. That would work just fine as well. So now going to the other questions, part D, according to the graph, what is the temperature change of the reaction mixture? So we note that it starts at 20.0 and it ends in between 32 and 33. So we would say 32.5. And we remember that delta T is always final minus initial. So 32.5 minus our 20.0, 12.5. And yes, that 0.5 is important for sig fig purposes. So 12.5 degrees Celsius is our answer for D. For E, calculate the magnitude of the heat energy in joules that is released during the reaction of 15.21 grams. Assume that the specific heat is 3.94 joule per gram degree Celsius, and the heat absorbed by the calorimeter is negligible. This is really nice. We don't have to worry about any heat loss anywhere else. We note that we're specifically asked for this to be in joules, and I'm given specific heat. And, we start thinking specific heat, and we just got delta T, and we're given a mass, and we look over on the equation sheet, and on the equation sheet, we notice Q equals MC delta T. So we're going to use it to solve for the amount of energy. So we had 15.21 grams, a specific heat value of 3.94 joule per gram degrees Celsius, and a change in temperature of 12.5 degrees Celsius. Now, notice this right here, we are just solving for the heat that is released, and it actually says released by the reaction. This is what happens for the temperature for the solutions in the container. So, if we grab a calculator, 15.21 times 3.94 times 12.5, and we get 749 joules for an answer. And 3 sig figs is what we used. 12.5 degrees Celsius was 3 sig figs. 3.94 was 3 sig figs. Even though that had 4 sig figs, 3 sig figs is the most that we're allowed to have. Part two is honestly the trickiest part of this question to me. Using the balanced equation for the reaction and your answer to part C, calculate the value of the enthalpy change. Okay, and here's the tricky part. It says of the reaction in kilojoule per mole, include the appropriate algebraic sign. So of the reaction, we're not looking for the delta H for the limiting reactant. We're not looking for the delta H of one of the other reactants or anything like that. We want it for the entire reaction itself. So our limiting reactant was NaOCl. And notice for the reaction, it has a coefficient of 4. The delta H of the reaction, okay, that would be representative for when 4 moles of that react. So we're going to have to pay attention to that. The other thing to look at is kilojoule per mole. They're helping us by showing us how to solve for the enthalpy. We're going to take our answer in joules and put it in kilojoules, and we're going to divide by the appropriate number of moles related to the reaction. So that would be 0.749 kilojoules for the number of kilojoules for the reaction. But now for the moles, well, remember, I told you to remember this earlier, it was 0.005 liters times 0.5 molar. It was 0.0025 moles of our limiting reactant. And then the reaction, it was a coefficient of 4. So we need to divide by 4, and we get 0.000625 moles. This will give us the enthalpy change of the reaction itself. So 0.749 divided by 0.000625, and we get 1,198.4 kilojoules per mole. But be careful. We were asked to pay attention to the algebraic sign. And it even says right here, for that is the energy that is released during the reaction. The reaction releases energy, the solution gains it. So we're going to have to make this negative, and we need 3 sig figs. So negative 1.20 times 10 to the third kilojoule per mole. That would be our answer for the delta H of this reaction. And to finish, it says this student repeats the experiment, but this time they double the volume of the reactants as shown. The molarities stay the same, but now it's 10, 10, and 10 milliliters. F, the magnitude of the enthalpy change calculated from the results of the second experiment is the same as the result calculated in E Part 2. Explain. We don't have to do any math. We just need to explain this. So notice, since the molarities stay the same and the volumes stay the same, you would get the exact same number of moles of reactants. It would be twice the number of moles of the original reactant. So when that happens, we'll get 2 times the original number of moles, and there would be twice the amount of energy released as well. Sorry, I put my little line in the wrong place. There would be 2 times the original amount of heat in kilojoules. Therefore, the number of kilojoules per mole would actually end up being the same. So to explain this result, you could just point out you would have twice as many moles, but you would also have twice as much heat released. Therefore, the final answer would turn out to be exactly the same. And now it wants the balanced net ionic equation for the given reaction. So if we come back and look at the original reaction, net ionic, we have practiced this in class. Anything that is aqueous and ionic, we break up. If you recognize an acid or a base, if it is a strong acid or a strong base, we break it up. Well, sodium hydroxide is a strong base. We're going to break it up. Everybody else here is aqueous. So we will have 2 sodium ions and 1 S2O3 ion. We'll have 4 sodium ions, 1 hypochlorite ion, 2 sodiums, and we will have 2 hydroxides. On the product side, and these would all be aqueous, I'm just getting through this on the quick side, video's getting a little long. We will have 4 sodiums, 2 sulfates, 4 sodiums, and 4 chlorines. And again, they are all aqueous. So this is our complete ionic. Little water out there is left alone because that's a liquid. That's the truth. We don't break that up. So we look. I have 2, 4, 6. I have 8 total sodiums and 8 total sodiums. So the sodiums cancel out, but nothing else does. Everything else, every species does undergo a chemical change. So S2O3 minus plus OCl minus plus 2OH minus yields 2 sulfates and 4 chlorine ions and one little old liquid water sitting out there on its own. And this would be the balanced net ionic equation for the given reaction. So quickly, the point distribution here. In number 1, it was 1 point for saying that chlorine was a positive 1. In B, it was plus 1 if you got 0.05 moles of our compound. And it was plus 1 for 7.9 grams for our final answer. For C, it was 1 point for saying NaOCl, and your justification had to some way tie into the fact that it had the greatest coefficient. Points for the other part, D, 12.5 degrees Celsius, merited a point. E, part 1, it was 1 point overall for 749 joules for an answer. E, part 2, if you paid attention to that tricky little part, and you took the 0.005 moles and then you divided by 4, that got you 1 point, and then you got 1 point for an answer of negative 1.2 times 10 to the third kilojoules per mole. And then F was asking for an explanation here. It was 1 point for an explanation that talked about how while the moles do double, well, so would the amount of heat generated, so there actually is no change to the delta H, and then 1 point for the net ionic equation. Thank you for going through this problem with me.